Today we're going to look at a bit of a lab improvement project that involves power supplies. The hobbyist has a couple of good choices, not including expensive benchtop power supplies that come in variable or fixed form. Those are really cool as an upgrade, when you move kind of past the hobbyist stuff into bigger gear. But to start out, we'll just kind of go over some of your options as a beginner, going from least awesome to most awesome. Starting out, you have batteries. And these are a good way to start out as their energy potential is pretty low, so if you short something out, it's probably not going to explode. They're also great for portable projects and things like that. Their downsides are, of course, capacity. You will drain these and then have to replace them. And as they drain, the voltage decreases, so they're not always the same voltage throughout their lifespan. That can throw some things off. Not the end of the world, but limited in that regard. Option number 2 is the old power brick. These are a good option as they are cheap, and as long as you can get a high quality one, you'll get decent voltages out of them, though you do have to be careful. I've had some, like this crappy Action Tech or Linksys ones, that say 12 volts, but they really push out more like 15 to 17, because it'll decrease as load increases, which kind of sucks. These are usually good for like 2 to 3 amps, so you can do a decent power project, but nothing too crazy. And usually the only voltages you'll really need for these that are going to be the most common are 12 and 5 volts. The big daddy option is the PC power supply, and this is what I've been using for a while, just with some cheesy alligator clips and a paper clip in the green to black terminals here to power it up. Ghetto, but it works very well. The advantage of a PC power supply is voltages. You have all the most common voltages you'll need for your projects: 5, 3.3, and 12. This is a Mac power supply, so it also has 25 for the FireWire. So that's pretty cool if you can find it for motors and stuff like that, but not necessary. The big advantage you'll notice with these is, you have a lot more overhead for current, so you can do 18.5 on the 5, 24 on 3, and up to 13 on the 12 volt line. So we can drive much bigger stuff with these. And in a decent power supply, decent quality, the power control on this is going to be much better. So the voltages coming out are going to be within a very strict tolerance. That's going to be much better than your batteries or your power bricks. Not as good as a dedicated benchtop supply, but dang near close enough starting out. The other disadvantage, or like the big disadvantage you get with these, is these cables are unwieldy and kind of crappy. And it isn't pretty. There's really no good way to attach stuff, unless you got Molex connectors all over the place, which aren't always ideal. So what we're going to do is we're going to focus on the PC power supply option, and I'm going to show you a way that we can take this, get rid of all this clutter, put a nice face on it, and some connectors to turn this into a really good, cheap, hobbyist benchtop supply. So we'll get started on this, and yeah, hopefully at the end we'll have something pretty cool worked out. Starting out, I went through my pile of power supplies and found one that had good specs and was from a respectable manufacturer. Then I took some quick measurements, whipped up a model in SketchUp of the front panel layout I wanted, and that's what we're 3D printing now. So once this is finished, we'll rip the guts out of the power supply, and then we'll start putting things together. There's our parts hot off the 3D printer, and you can see they turned out pretty well. I went with that 20% infill, which gives us that cool honeycomb effect and saves on a bit of plastic. And with the 5mm walls here, it's actually pretty tough, so awesome. We did have a couple of problems where some of these parts have just a little bit of bow to them, and that's because I moved my printer from one side of the bench to the other, and I didn't even think to calibrate it. So the bed isn't 100% level. But luckily these turned out well after 3 or 4 restarts, but it's just cheap plastic, who cares? I got final product out of it, that's all that matters. What we'll do now is I'll get out the gluing supply so you can glue these two halves together. And then once that's done, we can get them mounted to the power supply here. And then we'll do some wiring and test it out. So yeah, looking good. The gluing process should be pretty simple. We've just got a piece of old scanner glass here, and this is a really nice tempered optical glass that's very, very smooth. And of course, now that I touched it, we'll have to wash it again. Oops. What we're going to use for adhesive is just good old super glue. I've used this for a lot of other PLA parts, and you know what? It holds really, really well. So we'll give it a shot here, and it's one of those things, if this doesn't work, I can always print some new parts, and we'll try the epoxy instead, because I know the epoxy will not come apart. Just make sure we have plenty of glue. And if you ever want lots of super glue, if you have a Menards in your area, every so often in the paint aisle, they'll sell this super cheap red stuff for like 39 cents for a pack of 2. And so I literally buy like a peg of this crap for, you know, 10 bucks. And I'm good for like a year. So it's definitely one option. So get these lined up as much as possible. Because now we're just going to take this guy. And how about a massive battery pack? Just set on top to hold it straight like that. There we go. So I'll let that sit for a couple of hours and we'll come back and we'll see how it turns out. So there's our front panel after the glue is set. Now there's a bit of a gap you can kind of feel here, and it's got a little bit of wobble to it. But man, you can crank on that all you want and she ain't coming apart. So super glue plus PLA, awesome. So what I'll do now, I'll get the file out and kind of file down some of the ridges and mismatches. And then I've got a power supply here. We do have to take this apart, isolate the 12-volt rails, and then I do have to drill a matching hole for this and 2 in the bottom for the mounting of that front plate. So I'll get that done. We'll get this mounted up and start preparing the wiring. Alright, so we're ready to take this beast apart and get it ready. We need to drill a hole in this side for that front panel connection here, and we need to prepare it for rewiring because all this wire isn't going to work. I did give it a bit of a haircut here, but we really don't need this much. And I've got some fuses and stuff like that we're going to wire in, so yeah, we got to pop it open. Now, of course, when dealing with power supplies, you do want to be careful. There are some capacitors in here that can store mains voltage for, you know, quite a while after you pull it from power. So you don't want to go licking this thing or anything. What I find works best is to actually power the supply up. You know, either grounding that little green pin or running the computer it's attached to, and then pull out the power cord from it. And this will cause it to bleed the caps a little faster than normal. And then maybe let it sit an hour if you're really, really paranoid. Otherwise, just be careful what you touch while you're inside here. Don't just go, you know, grabbing stuff willy-nilly. And there's the inside of our power supply after we pull the case off. And I already did drill a bunch of new mounting holes for the front panel stuff. Just some extra screw points to secure it in. And then I chopped off all of this cable here. It's just laying in a pile on the workbench because we're going to desolder most of this wire out and then replace it with these guys, which are just some automotive blade fuse holders. And then we're just going to snip it, put one end down to the board, the other end on a spade terminal that'll connect to the front, so we have a nice fused connection. And we don't have this rat's nest. That's just like a fire waiting to happen if I leave it like it is. So I'll get that chopped up, or actually it is chopped up, but I'll get it unsoldered from the board, and then we'll put these in and button it all back up. There we are with the clean board. I've got all of these wires yanked out. and I cleaned up all of the holes as well. You did see that some of those required quite a bit of heat, especially like these grounded ones, or the ground connectors. And that's because you've got this huge chunk of copper in here on the ground plane that soaks up a tremendous amount of heat. I mean, not to mention these wires. That's a lot of wire to heat up, as well as the plug. So we really had to max out the iron, but hey, it did pretty good, and those cleaned up nicely. Now what I'm going to do is I'm going to grab our connectors that we're going to run through, and then we're going to connect them to the proper rails. And this one's nicely labeled. You can see, like here, we've got our first 12 volt rail, second 12 volt rail. We got some 5 and 3 volt down here, and back here as well. So it'll be real easy to figure out what we need to wire up. I'm just going to do one 12 volt for now, and then just test to make sure it's happy. And then after that, we'll wire up the rest and be good to go. I've put our power supply back in the case, and then we have our 12 volt, a ground, and then the power trigger here sticking out. And then I've got a 10 amp fuse running up to my multimeter here. And what I'm doing here is just making sure that we have at least one rail that's functioning after pulling out, all of the wiring in here, just to make sure we didn't zort something with the heat and pressure, and to see how it functions. I like to do it bit at a time when I do a project like this, just because it really sucks to, kind of do everything in batch and then find out, oh hey, you've got a fault. Then you have to start stripping back everything you've done to find the fault, or say, the worst happens and you start a fire. Well, that's a lot of work down the tubes. So we're going to just test in stages as we build this puppy, just to make sure everything's good. What I'll do now is connect it to the mains, and we'll see if we get any flames. No. Let's turn our meter on here. And then we'll connect our power trigger here, just to the ground with this alligator clip. Alright, fingers crossed. Oh, look at that. No smoke, no flames, and 12 volts coming out of it. So, perfect. Wiring complete, and we're almost ready to bolt this back together. We've got our 3-3, our 5, and our 12 volt lines run, and you'll notice we use some really thick wire here. This is like a 12 gauge wire, and that's because the original wires coming out here, if you remember, there's like 5 or 6 per bundle of the really small, like 18 or 22 gauge. So to make up for not using multiple strands, we use a thicker wire, and the 12 gauge is about the max that you can stuff through one of those holes, and still make it through the other side and solder it up. So it'll work pretty well. It'll carry enough current. We're not going to be running amps or anything nuts off of this power supply. It's just project stuff. We've got our nice little modified spade push crimp connectors that are soldered as well, so these should hold up very nicely. And then we've got 2 wires that I think really set these power supply projects apart from either a hack or a really nice one. And that's the 3.3 volt sense that runs down next to the 3.3 here, that 3.3 VS for voltage sense. What this does is allow all of the control circuitry to monitor the 3.3 volt line, not at the board, but at the actual connector. Your PC uses 3.3 volts for a lot of very critical components. It's used for the voltage regulators for your CPU, your memory, all of that stuff. So it's very important to sense the voltage at the actual connection to the motherboard rather than on the power supply, because there's voltage drop, from this wire, and you also get some drop in voltage when you have a high current device drawing on that wire. It's going to dip in voltage a little bit. So the controller senses right at the connector, and then it can crank it up on the board. If you don't connect this, a lot of times what you'll get is you'll get 3.4 or 3.5 volts off of this, not 3.3, because the board will overcompensate to make sure enough juice is making it here. So this will verify we get 3.3 at here, and we don't cook any of our Arduinos or sensors that use that voltage. So that's always good. The sense line is very important. And then another thing on the control board you're going to find, you'll have the green wire. We know that's power on, but there's also usually this gray wire connected. And this gray wire is the all good wire. So basically, when the power supply powers on, it waits for all of these rails to fire up. It goes, okay, I've got 3, I've got 5, I've got 12, voltages look good, and then it lights up this line. Something like between 3 and 5 volts, something like that. But this lets your motherboard know, hey, you've got all your voltages, you're ready to go. Until your motherboard sees this signal, it's holding your processor in reset, so the system will not start up. So what we're going to use this for is, not a motherboard, but I'm going to put the power LED on this. So when you flip the switch on the front panel, that little power LED we have at the top will light up using this line instead of just like a 3 or 5 volt line, so that we know, hey, we've got the right voltages at the posts and everything's hunky-dory. Because of that ugly split down the middle, I decided it was time to start experimenting with finishing 3D printed parts. So I just started with one of the handles, and after some primer noticed that it does get some pretty nasty ruts. So I just went ahead and hosed it down with more filler primer, used some of that red Bondo glazing putty, and wet sanded that, more filler primer on top of that, and then laid down our finish coat, and as you'll see here, it actually turned out pretty good. So I'm skipping ahead a few steps just because I want to get this done before the weekend is up in about 2 hours. So I've got it painted and I've got the posts mounted and wired up here. It's going to be a tight fit. There is not much room there, but that's okay. The finish turned out pretty good. I'm happy with that. This is some of that Rust-Oleum hammered stuff, that guy right there. And I really like this particular one. It's that weird kind of blue hammered look that reminds me of 60s industrial machinery. I don't know if you've ever seen like old printing presses and generators and stuff like that. Kind of have a weird finish like that, so it looks pretty cool. What we're going to do now is get the switch and the LED wired up to the power good connector here. And I'm going to show you a trick what to do when you say have like a bin of these just scrap LEDs out of computers and printers and stuff, but you really don't know what their voltage values are or what resistor to use for those, or like what the forward voltage is. There's a neat little trick you can do with a multimeter to figure that out and be accurate enough where you're not going to start this thing on fire or burn it out. So I'll show you that in just a sec here. This looks like a bit of a mess, but it's actually really simple. I metered out the power good line here earlier, and it turns out it's always 5 volts when it's working, so that's awesome. So we got our 5 volt line connected to our potentiometer here, and then the potentiometer is running to our LED. So what will happen is when we turn the knob on the pot, we introduce more and more voltage to the LED until it lights up. In between the ground on the LED and the power supply, our multimeter is connected to monitor the amount of current that LED is drawing. LEDs have 2 specs that you really care about. It's forward voltage and its draw at full bore. 99%, well, maybe not 99, but a vast majority of LEDs that you'll find of this type draw about 20 milliamps. And so that's what you kind of look for on your multimeter here. We're going to wait till it says 0.02. And once it's drawing that much power, we're going to pull the multimeter, actually check the voltage at this terminal, and that'll give us the forward voltage of this LED. Now the forward voltage is very important not to exceed, because that forward voltage is the point at which this LED basically becomes a short circuit, and if you run it like that for too long, you are going to burn it out very quickly. It's not designed for that, and you could even damage power supplies, drain batteries very quickly, that kind of thing. So you don't want to exceed that forward voltage, but we'll get that through this test rig here. So let's give it a shot. We'll turn our power supply on. There we go. And just watch the multimeter now as I turn this up very slowly. Let me see if I can do it so you can also see the LED. Nope, here we go. It's going to start drawing current here. 3 milliamps, 4, 5, 6, and you can see it's starting to light up a little bit. And oh, a little over. So crank it down just a little bit. There we go. Now, this is where having a second multimeter would be really handy, because I just yank it out, hit the lines, and see what we get. But what I'm going to have to do here is disconnect this multimeter, and then we'll see what we get here. So let's do that now. Turn our power supply off. And I'm going to move this just directly to one of our grounds. Pull this. Pull that. And then we won't touch the pot here when we flip it back on. There we go. Now if I just test the voltage on both sides, we should get our magic number here. So forward voltage on this one is 2.7 volts. Awesome. So now I just got to do some resistance calculations, what to do, you know, from 5 volts to get it down to the 2. And we'll have our resistor value and have a long-living, happy LED. Here's a look at the final product. Everything's bolted together, and I actually just finished using it for a little Arduino project, and it was perfect. Much better than using wall warts or crappy hacked up stuff. If I were to do this again, there are a couple changes I would make. The first would be making this a little deeper, just because stuffing all the wires and everything behind here was almost impossible. So a little extra depth wouldn't kill anything. It would make things a lot easier. The only other change I would make is swapping out these cheap eBay binding posts with some decent ones. I don't think we're going to have any problems with these melting or anything, but they are pretty chintzy, and the mounting required using some tighter hardware, because the hardware that comes with them is real crappy too, very bad on tolerances. But you know, we're just putting the banana plugs or the alligator clips directly in, so I don't think these are going to come loose or go nuts over time. But we'll look into changing these if I get antsy about it. Not a big deal. But yeah, there's another project off the list, and I think it'll see a lot of use down here until I build something better. Check out the details below, and I'll post the links to the Thingiverse files for all the 3D printed parts in case you ever want to make one of your own. And otherwise, hope you enjoyed. It was a fun little project, and I'm looking forward to getting some use out of it.